I'll start the timer.
Alright, bro.
But you've already started, bitch.
I'm like on initial, like I'm just typing up the initial stuff.
Yeah, but what? Why the fuck can't you wait like 2 minutes?
Because I know it's gonna take a while. I'm just trying to build up the logic.
So what, bro?
Okay, bro. Yeah, let's get started.
Path with minimum effort. Oh shit. Oh, okay. 25 minutes or 20 minutes? What?
Yeah, let's do 25 minutes.
Why, bro? Why not 20?
Do 20, bro. So the thing is, if it would be done
I've
in
started 25.
25 minutes, it would be also the same for 20 minutes.
Okay, I've
20
started
minutes
now.
won't make a difference.
I've started the timer.
Uh, effort, whatever the current effort goes into that.
Oh,
What happened, bro?
now I understand. I was not able to understand what the fuck this maximum absolute difference meant.
Hmm.
Yeah,
Now you do, right?
yeah.
Nice. Next current effort. This thing.
Holy shit. That's fucking complicated.
Current effort. Hmm. If you want to bend it from this to this.
The timer is up, by the way.
Okay, bro. Yeah, I was not able to solve.
One second. I'm gonna try one.
Yeah. Well, okay, bro.
Yeah,
You got it.
I'm trying. I'm trying to implement DFS in like one second. Oh, fuck. No, bro, I don't think so.
Yeah, bro. I think I did look up how to solve this. So you search up heap Q, and
Oh
you.
shit, bro. I was thinking of doing something like that.
What is heap Q?
Like I don't remember, but I opened my notes and I was looking at
Yeah. So
heap sort.
heap sort. Yeah, yeah. So we will use heap sort since we have to store our efforts in a binary form, like lowest to maximum, and we have to pop out our next available element based on the efforts that we have to open. So we have to always go for the minimum effort when we're trying to traverse. So your approach was like correct. We still have to use BFS approach for this.
Mm-hmm.
You can use DFS. I use BFS. Like depends upon person to person. But yeah, that's the only thing. Like while we are traversing, we have to always traverse via selecting the minimum effort row or effort block that is adjacent to it.
So you used min heap.
No, dude, just like a heap push and heap pop. Not
Yeah, but there are two types. There is one min heap where like the parent is smaller than its child, and max heap is where the parent is larger than the child.
min heap.
So probably min heap.
Yeah, but like in the code, it does not talk about any min heap or max heap in Python.
Default in Python is min heap
Yeah, so
until
yeah,
you
that's what we
specify.
went with. Yeah, that's what we went with.
Insertion and removal both take O log n shows up when you repeatedly extract the smallest largest item, maintaining a top K on bottom K set of values. Real-time ranking need to sort on the fly. So given 2D blah 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 distance needs to return K closest first to the origin left K closest. Let me ask ChatGPT. Oh, it explicitly says it's Dijkstra.
Yeah, but like I think the approach is similar to BFS, like the algorithm.
Mm-hmm.
Yeah, bro. What
Yeah,
is?
I'm reading it.
Where are you reading it?
Can't you see my screen?
Yeah, I can see your screen, but you're not scrolling down. Like we are at the same place for a long time.
Oh, wait. Yeah.
But we have to normally add edge cost 5 plus 3 equal to 8, effort equal to maximum edge encounter. So instead we use current.
Extras. But the extra normally adds cost, correct. Classic extras is new cost, current cost plus H cost. A5, B3, C. The cost is 5 plus 8, but our problem defines the path, effort differently, maximum edge encountered. So new max of current effort, comma, edge effort. Oh, also in Python, can we call the max function independently and sort out which is the max value?
Yeah.
Okay. Let's walk through the street. BFS you stored R comma C, R comma C distance, row column, best effort required to reach your DQ, heap Q, effort, row Q, row call. was a min heap. Yeah, that's what I was talking about.
Hmm.
Min heap. Why is my laptop so slow today? What the fuck is going on?
Memory cache.
Uh, but Dijkstra needs to always process the currently cheapest first RC distance. So instead of DQ, we use heap Q. Min heap, state stored, effort row call. Notice effort is first. Why Python's heap compares tuples starting from the first element. So 212701432 gets processed in this order 247. 247? Exactly what Dijkstra wants. I didn't understand this. Did you understand this?
Yeah.
What is this effort row call? Where
So
is this?
we go to the question.
Yeah,
There is a route effort. Like read this line. That is over here. A route's effort is the maximum absolute difference in heights between two consecutive cells of the route. So you have two cells, right? So they have, so whatever the difference, so 3 minus 1 is gonna be
is
the
2.
effort that's it's gonna take from moving from one cell to another cell,
Yeah,
right? So that's what we have over there in our code. Like if you go to,
effort.
yes, so that's what effort defines, like for
Mhm.
each and every move, right? Because since we are moving in a direction, so we have to always go for the
But
minimum.
what does this mean? So if these are the three, like if this is the grid,
This is not.
right?
This is the. So yeah, yeah. Go ahead. Yeah, this is the grid. Okay.
Yeah, so it says get. So this gets processed in this order 247. What does this mean? 2, 4, and then 7?
Yes. So it
What?
follows the
How?
minimum heap structure. So two is going to be your minimum effort, and then four,
Yeah,
and then seven. So what is the index of those? Like what will be the, so let's say you are at two. You
0,
are,
comma 0,
no, no, no.
1, comma.
No, not that. Let's say you are at 1 comma 2 index. You have to plan 1 comma 2 index in the grid.
Plan?
Do you see this 1 comma 2 on your first row? 1 comma 2 is the index of your grid, like the original grid that you have. 1 comma 2, you see over here 1 comma 2.
What are you pointing at?
Like
1, comma 2?
yeah, 2 1 2 1 comma 2.
Oh, 1, comma 2, this.
Yes.
So,
So what is this? Do you know what is this?
what is this?
This is the index. This is the index of your grid, the main grid that you have. 1 comma 2 row comma.
Oh, okay, this row call and oh, okay, okay. Oh, so 247. But why is 247? Like,
Because that's how many he processes your heap.
but how? Like, what is the logic?
Dude, the heap does that for you. The logic is that, like, main heap. So two, so you have your two.
Because 2 to 4, going from 2 to 4 is less effort than 4 to 7. Is that what you're saying? Or 2 to 7?
So you will, so the way you will go from in the grid, like if you go open the grid again, open the grid. Yes.
Yeah.
So what's one? So what will be 1 comma 2? So if you are at 1 comma 2 index in the grid,
Uh, 8.
8. Let's say you are at 1 comma 2. So
Yeah.
now if you want to move in any direction,
Yeah.
Would be the so in any direction. How will you select? You will select based on the minimum effort
Yeah.
that it will take, right?
Yeah.
When heap sorts out your already explored indexes by the effort it's gonna take. So let's say you are at 8.
Yeah, that's what I'm asking, bro. Like 8 minus 2 is gonna be 6, 8 minus 3 is gonna be 5.
Yes,
So 8 minus 3 is gonna take less effort,
yes,
right?
yes,
So according to Menheap, it will return 3.
yes,
Okay. That's what I was asking.
yes, yes.
So if it is at 2,
Hmm. No, it's
but
at,
sorry, if it is at 1 comma 2,
yes,
and to go from 1 comma 2 to 0 comma 1, it's gonna take effort of 7.
yes,
Okay. And that's why it organizes it like this
yes.
because okay, 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 got it. BFS, this is a major addition to your arsenal. BFS is Q's DQ. Process states in discovery order. Dijkstra heap. Process the cheapest known state first. Q is ABC oldest first. Okay, yeah, first in first out. So oldest first. And heap is cos 2, cos 5, cos 9, cheapest first. Ah, cheap. Dijkstra is cheap. What does dist mean here? Effort is equal to float into CO calls
So this is the
for.
matrix that you're trying to create for your effort for each and every block. Uh, Like you have our original matrix, and then we are going to replicate the same matrix, but instead of putting in the values of the indexes, we are going to put the efforts that it is going to take. So we will always have the minimum effort that will be loaded inside our effort matrix. So like if you take a look over here, so
Wait, 1 second. Effort is equal to. This is a list.
no, this is a matrix.
Oh, this is a matrix. Okay. And then there is another float of inf. What is this? Inf?
Infinite, that means that the element has infinity value max.
This
Yes,
this element
yes,
in an infinity into column.
yes. So that means that many columns are generated if you're doing infinity into column. So if you are
Why are we doing that here?
to create the matrix for the effort, like look at the line below.
For every cell, effort R, comma C. So for dash in range of rows, okay, so it's gonna take in rows, and however many rows are there, it's gonna print out an effort.
Yeah.
Okay, smallest known maximum effort to reach R, comma C from 0, comma 0. Start is equal to 0 effort. Everything else is infinity. Effort 0, comma 0 is 0. Yes, yes,
Mhm.
yes. Initialize the distance slash effort matrix.
Yes, so this is what I was talking about. This is the matrix.
Okay, so initially example, it's gonna be infinity.
That is the maximum effort, right? But
Hmm.
what we are looking for is a minimum effort, right? So
So
now,
effort 0, comma 0
so for
is
this,
0.
it will be zero always because we are. This is our starting index. From where
Uh-huh.
we can start. Now,
Yeah, so we are setting this manually.
yes, we are setting this manually.
Okay, and then initialize heap.
Yes, so this is our initial point for heat. Therefore,
Hmm.
if zero row comma column is also gonna be zero.
And how is this defined that this is effort, this is row, and this is column?
Like you can, so but
They didn't define it over here. Or
you
is it? automatically
You can
assume.
initialize it at any point. Like that's the magic of heap. Like you can initialize it. That's for so effort row column. That is for your internal reference.
Okay, 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 okay,
Right.
okay, okay. Okay, the extra loop is while heap
So until the heap is
current
not emptied out.
f r comma c is going to store heap q dot heap pop heap. Okay, so it's gonna initialize it with zero values, right? So
Yes.
this is gonna have zero, zero, zero.
Yes.
And then r comma c now compare bf. Oh,
We are looking into Dijkstra's.
oh yes, yes, yes. Okay,
Yes.
effort rc. Okay, I get this now. Very similar architecture. Okay. Explore neighbors for dr, comma dc in directions. Nr yes, 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 yes. Nr is smaller than 0. Nr is greater than equal to rows. Okay, this is the same thing as the thing that we were trying over
Yes.
here with BF.
Yes.
This one, if
Yes. Yes.
0 and all.
But it's not basically checking. It's saying that if you can, it's checking that hey, if any of the condition is true, then we won't
Uh-huh.
do anything. But we can like modify it accordingly and put it in. Now this is where our edge effort kicks in. This is
Okay, so
model logic.
edge effort is equal to ABS height RC minus height NC. The most important line, we already had some maximum effort getting to our cell, current effort 4. How is it starting with current effort 4?
Where the
Oh, suppose current effort is 4. Okay.
now the edge.
And this next edge cost, edge effort is 2. Then the whole path effort remains 4. So new effort is equal to max
Of
of current effort and edge effort. Got it.
yes.
Another example is current effort is 4, next jump is 9, so new effort would be 9 because the worst jump is now 9. Okay, relaxation. This is a very important extra step. Suppose we previously knew best effort to reach a cell is 8, but we found another path requiring new effort 5. Obviously, 8 is greater than 5. We found something better, we update. If new effort is smaller than effort of NRNC, then effort of RRNC is equal to new effort. Okay, heap q dot heap push heap comma new effort. Okay, so this is gonna update the heap with the new effort.
Yes.
This is
And
called relaxing
it
it.
goes in over there, it's gonna be rearranged by minimum effort. Like whatever the
Oh,
minimum effort is gonna be, it's gonna be rearranged in that manner. And that's how we will always know that we are forwarding in a correct direction.
okay, so generate Dijkstra if new cost is smaller than distance of neighbor. Distance of neighbor is equal to new cost. So if new effort is smaller than effort of NRNC, effort of NRNC is equal to new effort. Early termination. When we pop the destination, if R is equal to rows minus 1, C is equal to column minus 1, return current effort, we can immediately return Y. Because the heap gives us the lowest effort state currently possible. Okay, so this is where the termination happens. This is analogous to BFS. First time BFS reaches destination at the correct level, shortest path. First time destination is finalized by min heap cheapest path. Okay, so this is the complete solution. Let's run this and look, inspect over there. Okay, we're missing one subtle optimization.
Go to the top here. It's gonna work, bro, definitely.
Yeah, okay.
But the most important thing is that you keep optimization.
1 second. Rows, columns, directions, effort. Float in effort 00 is set manually at 0. Heap is set manually at 000, while heap is current effort, comma r, comma c is set as heap and heap pop dot heap q dot heap pop, and this heap is okay. If row is equal to row minus 1, row minus 1 is gonna be that, and c is equal to column minus 1. Return current effort. Okay, so this is basically doing this return current effort. Okay. So it's gonna exit over here if it realizes that we have already reached here with the current effort.
Yes.
For dr comma dc in direction nr r plus dr c. Okay. uh, nr equals to r plus dr c plus dc, and if nr is smaller than 0 or nr is greater than equal to rows, or nc is smaller than 0, or so if any of these things are true, then continue, right? Bro, why the fuck are you looking at your phone?
I was trying to go through something. But what? Yeah, come again.
I'm saying if any of these things are true, then it's gonna continue.
Yes, it's gonna skip everything else.
Yeah, continue. Edge effort is equal to abs. What is
Ab-
abs?
Absolute. Like it's always gonna be the positive value.
Oh, positive. Okay. Heights RC minus heights NRNC. So this means 2 minus whatever, like value of this minus value of this, and then edge effort is going to be calculated, and then new effort is going to be max of current effort, comma edge effort. Okay, got it. If new effort is smaller than effort of NRNC, effort of NRNC is the new effort. Mm-hmm. And update the heap. Heap q dot heap push heap.
So now we are updating it because we have found a minimum new effort.
Mm-hmm.
Otherwise, we won't update. We are only pushing in minimum values into the heap.
Where are we? Oh, output two. Okay.
Yeah. So like we are returning zero in case we do not find a minimum value. Otherwise, it will return infinity. Because if
Hmm.
you are not able to reach the end of
Where are we returning the output though?
like go down like on line 27 and 28, we are returning the output.
Oh yes, current effort.
So that's how we are doing it, and that's the way because if we need to. Our goal is to reach end of the array. So we are exploring each and every direction, and while we are exploring and traveling along,
Got it. Yeah, I understood the whole code. Yes.
nice.
And but we are missing one subtle optimization. Initially, reach x with effort 10, heap 10, comma x, discover better route. Well, let's try and submit this. Uh-huh. Discover better route. Eventually, 10, comma x may also get popped, but it's stale, so production quality extras actually checks if current effort is greater than continue because okay, ignore the old heap entry. What is this doing? Let's see. What?
Dude, I'm telling you, these runtimes where server
I see.
very very.
Okay, so this is same, this is same, this is same. Stale entry if current effort is this. So this is also same for dr comma dc. In directions nr, yes, yes, same. Effort is equal to absolute of this, same. New effort is also same. If new effort is smaller than this, effort is okay. What? It's all the same. What is it? What changed? Ignore the old heap entry. What is it saying? What changed over here? And then we already know the better route. What is it saying still? If current effort is greater than this. Oh. So if current effort is smaller than effort, then it will break.
It won't break, it will continue. If the current effort is less than,
Yeah, effort. It won't continue, right?
yeah, it won't continue.
So it will return whatever value it has.
It will return zero.
And then what will happen?
That's it, the program will break.
I
But
don't
if
know what optimization this has done. Like what has optimized over here? This part.
if current effort is greater than effort R of C, then we continue.
But I understood the code. I don't know what this is just. I
Hmm.
don't know. So yeah, Dhanush M says hello guys. Hello man.
Brother,
Hello brother. Do you want moral support, brother?
no moral support चाहिए था मेरे अब तो.
Okay, I ended the stream.
Whatever.
Oh.